Today, the plan is to talk about this example of the binomial success probability. And next, we'll talk about different priors distributions. Specifically, we'll talk about Jeffrey's prior and objective prior formulation, how we can do that, and we'll illustrate it using binomial example and the Poisson example. So possibly next 2 days, like today and the next lecture, we'll talk about these things. So this is repetition. Hormone replacement therapy is used to reduce hot flashes and night sweats during the onset of menopause. Let theta be the proportion of people who experience different side effects after taking HRT. Suppose that in a clinical study, 44 people experience some type of side effects out of a sample of 100 people. Suppose that a beta prior is to be used, and we'll look at the effect of choices for A and B. What are those A and B? A and B are the two parameters of the beta distribution, beta prior distribution, on a Bayes estimate of theta. Bayes estimate, so we'll talk about posterior mean as our estimator. So the classical point estimate of theta is the MLE. Classical estimate is the MLE, which is the number of successes divided by total number of observations. Number of successes, quote unquote, means here by success I mean number of people who experience that side effect divided by the total number. 44 over 100 is the maximum likelihood estimator of theta in this context. And if I use a beta prior distribution with parameters A and B, then the posterior distribution you already know, again a beta distribution with parameters y plus A, and the second parameter becomes n minus y plus b. With the mean of the beta distribution is a ratio. The numerator is the first parameter and the denominator is the total of first and second parameter. So if I apply this formula, it turned out to be 44 plus A divided by 100 plus A plus B. Now for different choices of A and B, when A and B are equal to 1, that gives you uniform prior distribution. Prior is uniform over 0 to 1. Then the Bayes estimate is 0.441. When it is 1/2 and 1/2, it is a particular type of non-informative prior. Let me show you the picture. So the first one is the blue shaded area is the prior distribution, uniform prior, as you see. The second one is the prior had parameters 1/2 and 1/2. It looks like a bathtub shape, right? So it's not purely non-informative. So that is why I say a type of non-informative prior, because what you see non-informative means you do not give preference to any particular value. Over here, you are giving preference to lower values and the higher values in the bathtub type of prior distribution, right? The third one is where A equal to 1, B equal to 2. This prior having mean of 1, 3 prefers lower values. Okay. And then A equal to 20, B equal to 40, an informative prior with a mean of 1/3. So on and so forth. And what you see how the prior distributions are impacting the posterior mean. Now, if I give prior distribution A equal to 40 and B equal to 20, an informative prior with the mean of 2/3, then the Bayes estimate becomes 0.525. So this is the one that is impacting too much to our inference, right? Originally, maximum likelihood estimator was 0.44. From there, you have a shift almost about 18 to 20% change in the parameter estimate because of the prior distribution. So I think this is the one here. The prior distribution is like this. Okay, you see what happened is this particular prior, not only shifting, the prior mean is shifted towards right, but it has very small variance. Because of small variability, it is actually dragging too much the data information towards the prior distribution. So what is the learning from this experiment? The learning message or the outcome is, if you have enough data, then you should not, you do not need to use very strong prior. Strong prior means the prior with a very small variance. Okay. If you have really strong faith on that prior, you are very confident that your parameter estimate should be in that region, then you use that prior distribution with a very small variability. But if you are not very sure about the prior distribution, then you allow more flexibility in the variance. That means larger variance will be more accurate, appropriate in this scenario. Next, we talk about predictive distributions, the marginal distribution of y, where you integrate out the unknown parameter with respect to the prior distribution. This is the marginal distribution. This is called prior predictive distribution. And another distribution, we call it posterior predictive distribution, is the distribution of a future observation given the observed data. This is called posterior predictive distribution, and this is the most important. Most important thing is how you can formulate the distribution of a future observation based on what you have observed. And that distribution is obtained as follows: P of y tilde given theta and y times P theta given y. What we do is that we multiply the data density given the parameter with the posterior distribution of the parameter. The second component is the posterior distribution of the unknown parameter given the data. Remember, this y, little y, is the observed data, and y tilde is the future observation, is not observed. This distribution could be used to predict a value of y tilde, future observation, given that uppercase Y is observed to be this one. So the realized value of the data is little y. Then we can use this distribution. Now, when we wrote the posterior predictive distribution, we kept this formula very general, conditional on theta and y. But often what happens, conditional on theta, any data does not depend on the previous data. Therefore, the formula reduces to this form: P of y tilde given theta times P theta given y, and you integrate over theta. Note that this distribution is generally different from the plug-in prediction. Plug-in prediction is you have the distribution of y tilde, future observation, given theta is equal to theta hat. It could be the posterior mean or something, where P theta y is replaced by a point mass at the estimate theta hat. Thus, uncertainty in estimating theta is ignored and the predictive intervals are too narrow. And I'll show you through one example that in some cases you get this distribution same as this one, but in some cases they are different. So let us talk about the binomial problem. So for the binomial beta case, binomial beta means data are coming from the binomial distribution and the prior distribution is coming from the beta distribution. Obtaining the posterior predictive distribution even easier. So for a future observation, y tilde, it could be 1 or it could be 0. So let us calculate probability that a future observation y tilde is equal to 1 given the observed data. First thing is, what is the probability that y tilde equal to 1 given theta? It is theta. So we plug in theta and multiply it with the posterior distribution of theta given the data. And it is what? It is the posterior mean of theta, and it is equal to a plus sum of yi divided by n plus a plus b. Likewise, probability of y tilde equal to 0 given data is equal to 1 minus probability of y tilde equal to 1 given observed data. Now in the previous example, with the uniform prior, that means a equal to 1, b equal to 1, we observed this probability to be 44 plus 1 divided by 100 plus 1 plus 1. 44 because number of successes was 44 and a equal to 1 and b equal to 1 and n was 100. So it came out to be 0.441. Now let us also calculate the variance of y tilde given y. And variance, how do you calculate the variance? The variance of a Bernoulli random variable is probability of success times 1 minus probability of the success. Now the success probability came out to be 0.441. So it is 0.441 times 1 minus 0.441 is equal to 0.2465. Now let us calculate plug-in prediction. Plug-in prediction with theta hat being the posterior mean, then probability y tilde equal to 1 given y and theta hat being 0.441 is simply 0.441. And let us calculate the variance of the distribution. It turned out to be 0.2465. So for this particular example, plug-in estimator of the posterior predictive distribution and the actual posterior predictive distributions, they are identical, but it is not guaranteed to be identical. Next issue is that uniform prior distribution. We used uniform prior distribution in this example, and it was non-informative, right? It was not giving any preference to a particular value of the parameter. But there are some issues. A uniform distribution on the parameter space initially seems a natural non-informative prior for theta. However, this results in the following issue when considering other parameterizations or transformation of the unknown parameter. What are the issues? So suppose I have a function of the parameter theta. Let's say g theta is the function. with g being a one-to-one function, then the implied prior for g theta is not generally uniform. So although theta had a uniform prior, g theta, this transformed parameter, does not have a uniform prior distribution. So what is the prior distribution of g theta? The prior distribution of g theta will be of this format. If we assume a uniform prior for theta, that means p theta is proportional to 1, then the first quantity of the right hand side of this expression 4 is a constant. However, the second quantity is only constant if g is a linear function. Otherwise, it will be a function of theta or g theta. And this is a problematic because we might have chosen a uniform prior if we had started with the parameterization in terms of psi. The so-called Jeffreys prior provides a solution to this issue. So regular uniform prior is not invariant to the transformation. Therefore, we have a better choice, and that better choice is the Jeffreys prior. Jeffreys prior solves that problem. It says if it is uniform, it is non-informative with respect to one expression of the parameter, then it is also non-informative with respect to a transformation of the parameter. Okay, so let us talk about a specific example. Suppose we use a uniform distribution on the binomial success probability theta. That means the prior density for theta is uniform. That means the density function is equal to 1 when the variable lies between 0 and 1. Otherwise, we can write p theta r proportional to 1. Now let us derive the prior density for the odds of the success. So we talk about Bernoulli random variable or the binomial distribution. There is a parameter called success probability. Often we talk about the odds of success. Odds of success is the probability divided by 1 minus the probability. So how about we derive the prior distribution for this guy psi when we have uniform prior on theta. So if I take the derivative, calculate the Jacobian, it turned out the prior distribution on the odds parameter is 1 over 1 plus s square. And it is seen that this density of psi density evaluated at this point S is no longer a uniform distribution, which contradicts our intuition that if the prior for theta is non-informative, then should be for psi. So you get informative density for the odds of the success. Jeffreys prior. So now we introduce Jeffreys prior. Let y be a random variable or the observation vector with the density py given theta, and let theta be the unknown parameter. Jeffreys prior is defined as the square root of the information matrix. What is the information matrix? It is the double derivative of the log likelihood and take expectation, put a negative sign before that. Now this is the information. If you have a scalar parameter and if you have multiple parameters, a vector of parameters, then the technique is you take the determinant of this information and take the square root. determinant of this information matrix. So for a scalar valued parameter theta, it is all right to define in this way. Is also called the Fisher's information for theta. And this Jeffreys prior maximizes the Kullback-Leibler divergence between the prior and the posterior, which can be viewed as the amount of information brought by the data. And so Jeffreys prior minimizes the Kullback-Leibler divergence between two density functions is defined as follows. One way of defining the divergence. And here you can see this is the numerator is the posterior density and the denominator is the prior density function for the parameter. For a vector, as I said, it will be determinant of the information matrix and then take square root of it to obtain Jeffreys prior. Invariance of the Jeffreys prior. The Jeffreys prior is invariant with respect to one-to-one transformation. For example, if psi is the transformed value of the parameter theta, and this is the transformation g theta is used, and if the prior for theta is Jeffreys prior, which has the following form, then the prior for psi will also follow this structure. Now I leave this part for you to understand. It is calculated here. It's very simple calculation, just the derivative. Okay, you just look at it and let me know if you have any questions. Now I will talk about Jeffreys prior for the binomial experiment. So in order to calculate Jeffreys prior, what you need? You need the data distribution. You will be calculating information matrix, which is double derivative of the log likelihood and then take expectation. So log likelihood calculation means you need the model, data generating model. So assume that the observations are coming from a binomial distribution with success probability theta and the number of trials n. Either I say that or I can say the observations are IID in IID Bernoulli random variables. Either I say that or I can say the observation is coming from a binomial distribution. Both will give you the identical likelihood function. So the likelihood for binomial distribution is n choose y theta to the power y 1 minus theta to the power n minus y. This is the likelihood given data. So I'll be writing it here. If I take the log, or sometimes we write it py given theta. So this is py given theta. If I take log of py given theta, it is log of n choose y and y log of theta n minus y log of 1 minus theta. Now, over here, I have written that expression without keeping n choose y term. N choose y does not involve our parameter theta. And what I'm going to do, I'm going to take two derivatives of this expression with respect to theta. So that constant term free from theta will not contribute anything. Therefore, from the very beginning, I just omitted that term, n choose y term. So if I take the derivative with respect to theta, it turns out y over theta minus n minus y over 1 minus theta. Take one more derivative, it turned out minus y over theta square minus n minus y over 1 minus theta square. And keep in mind what we need to take double derivative of the log likelihood, take negative sign, add a negative sign, and take expectation. So add a negative sign, we did it, and then expectation. Now expectation of this quantity involves expectation of this guy. Y is the random variable, right? So y, if it follows a binomial distribution, its expectation is n times theta, and expectation of n minus y is again n minus expectation of y, which is n times theta. So it is n minus theta. So after cancellation, you get n over theta times 1 minus theta. So the Jeffreys prior for theta is proportional to so since it is, I'm writing proportional, so I can omit n even, right? I do not need to write n. So it is a theta to the power minus 1/2 and 1 minus theta to the power minus 1/2, right? This is the Jeffreys prior. Now, can you tell me what is this? Can you identify this distribution? If the distribution is density function is proportional to this, what is the family? Which family does it belong to? Exactly, it belongs to the beta family. Which parameter? I can write theta to the power 0.5 minus 1, right? And 1 minus theta to the power 0.5 minus 1. 0.5 minus 1, 0.5 minus 1. So beta half and half. So theta follows beta 0.5 and 0.5. 0.5 and 0.5. Now 0.5, 0.5. Is this, right? We have seen it before. The bathtub type of curve, bathtub type of density function is the Jeffreys prior, right? So this Jeffreys prior is informative in this context, right? Jeffreys prior is informative, but it is an objective prior. that it does not depend on subject's choice. It is determined objectively and transformation invariant. So it is not uniform. It is not non-informative all the time. Remember, in this particular case, it is informative. In some other cases, it will be non-informative. Improper priors. The prior in the previous example is a proper prior. That means if you integrate out the prior distribution over the domain of the random variable or the domain of the parameter, then it is equal to 1. It is a proper prior distribution. Unfortunately, Jeffrey's prior for other likelihoods is often improper, meaning that when you integrate it, you don't get a finite value, you get infinity. Many people don't mind using improper priors. Prior density, although we are talking about prior density, it is not a probability density function when it is improper, right? If it does not integrate out to 1, then it is not a pure density function. So many people don't mind using improper priors. However, everyone agrees that doing so is okay only if the resulting posterior is proper. We don't mind using some improper quantity as the prior distribution, but the resulting posterior distribution, we need to make sure that is a proper density function. If it is not a proper density function, then I cannot calculate mean, variance, uncertainty quantification, nothing will be meaningful. Therefore, what matters is the posterior distribution. So we need to make sure in order to have we need to have this quantity finite for the posterior distribution to be proper, because this is the proportionality constant. It goes in the denominator of this posterior density function. Questions? Okay, so now let's talk about the Poisson data example. The Poisson distribution is a popular distribution for count data. The Poisson distribution with mean theta has the following probability mass function: e to the power minus theta, theta to the power y over y factorial, and the possible values of y are 0, 1, 2, all the way up to infinity. The parameter space theta must be positive, so it is 0 to infinity. Here P y given theta denotes the probability that Poisson random variable y takes on this little y. So instead of writing this entire expression, we'll be using this simple notation P little y given theta. Now suppose that the interest, this is one example, interest is in the blemishes in the plastic film process. Data are collected once an hour on the plastic film, and area is cut out and the blemishes are counted. The area in centimeter square and the number of blemishes are recorded. Suppose that the quality requirement requires 0.8 or less blemishes per centimeter square. 0.8 or less blemishes per centimeter square. What is the chance of observing 6 or more blemishes in an 11 centimeter square area? So the first part is not Bayesian, okay? So this is about just simple Poisson probability calculation. to get familiar with the Poisson distribution. No Bayesian here. Let y be the number of blemishes in 11 centimeters square, and under the Poisson assumption, on the number of blemishes on every centimeter square, this is an important property of the Poisson distribution. So Poisson random variable must be defined on some unit. Okay, so that unit could be unit interval, unit area. Okay, so here it is on unit area, it is defined every centimeter square. On every centimeter square, the number of blemishes follows a Poisson distribution. So over 11 centimeter square area, it will again follow a Poisson distribution, but its parameter will be multiplied by 11. So it will be 11 times 0.8, which is 8.8. Now, I want to calculate probability y greater than equal to 6. The number of blemishes will be larger than equal to 6 is equal to, you just need to specify the parameter value and you can calculate it in R or in any software. It turned out it is 87%, 0.87. Now for inference about the parameter theta, we need the likelihood function. So far, there is no inference. The first part, not an inference problem. This is a pure probability calculation. Assuming your theta is known, theta, which is the number of blemishes per unit area, is known, which is given 0.8. Next part is, suppose I want to make inference about the parameter theta, number of actual number of blemishes per unit square, theta. So what would that be? So this is observations. If you have n observations, then and if they are independent and identically distributed observations, then it will be the product of the probability mass functions evaluated at those observed values. And this is the probability mass function for the Poisson distribution, taking product and putting all terms together. I can write theta to the power n times y bar. What is y bar? Y bar is the average of y1, y2, yn, and e to the power minus n theta. And there is a term involving purely of data. That term I call it cy. It does not involve theta. Now, to find the classical estimator of theta, I know this is something you have already learned in your previous classes, but to give you the entire context, to give you the complete picture, I just noted down all the steps. If you want to obtain the classical estimator, what should you do? You can do maximum likelihood estimator. You can obtain that. For that, you take the logarithm of the likelihood function, take the derivative of the log likelihood, obtain the gradient and set the gradient to 0, solve for the unknown parameter from the gradient equation. These are the steps to obtain the MLE. So this is the log likelihood, this is the gradient, and set the gradient equal to 0, and then solve for theta. So if you solve for theta, theta had turned out to be average value of the observations, y bar. Next, we will talk about the Bayesian inference. Recall the likelihood of n IID Poisson observations y1, y2, yn is this quantity p data given theta, right? And it is theta to the power n y bar e to the power minus n theta. I particularly omitted the term cy, because that involved only the data, no theta was involved. Remember, to figure out a conjugate prior distribution, you need to look at the functional form of the likelihood involving theta. Theta is the parameter, and to figure out that conjugate distribution, this is the most important component. Now suppose that for our Poisson data, we use a gamma AB prior for theta. Gamma prior distribution looks like this: theta to the power a minus 1, e to the power minus b theta, where a and b are positive constants. Now tell me, is the gamma prior the conjugate prior for this problem? Yes, it is the conjugate prior, right? Because if I use this prior distribution with the likelihood given here, then the posterior distribution of theta would look like theta to the power something times e to the power minus some constant times theta. It again is a gamma random variable, right? So gamma distribution is the conjugate prior distribution for this problem. And it turned out that it is the gamma, the posterior is a gamma distribution with the parameters a plus n times y bar. And the second parameter is b plus n. So the posterior is this gamma distribution. So both the prior and posterior belong to the gamma family. Hence the gamma distribution is the conjugate prior for the Poisson data. Questions? Please go ahead.
That second, is it equal to that value, or do we need to provide some constant of which?
That's a very good question. So you obtain the posterior distribution in this format, and then based on your knowledge of some known distributions, you can easily say that it is the gamma distribution. You do not need to show us the constant of proportionality for these known distributions. Did I answer your question? So we talked about conjugate prior distribution calculation. Let us calculate now. Let us focus on Jeffreys prior calculation. Okay. Jeffreys prior. Why do you care about Jeffreys prior? Because this gives you an objective prior distribution. Okay. One is conjugate prior, but conjugate prior is informative most of the time. But Jeffreys prior is invariant under transformation. So another way of making inference. And you have seen that depending on your prior distribution, your inference could be different. So we need to be aware of all different prior distributions. Depending on our need, we can use different prior distributions. For Jeffreys prior, we need the information matrix calculation, Matrix, the term matrix we'll be using if we have multiple parameters. So for a single Poisson observation, y, the log likelihood is this Poisson log likelihood, and the derivative of log of the probability mass function is equal to this. Double derivative is equal to minus y over theta square. Thus, the Fisher's information is negative expectation of the double derivative. So it is negative, and negative makes it positive. Expectation of y will be theta over theta square. It turned out to be 1 over theta. So Jeffreys objective prior is p theta, which is square root of information, which is theta to the power minus 1/2. Now, is it proper? Is the Jeffreys prior proper? Let's verify. So prior density, if you integrate the prior density over its domain 0 to infinity, it is equal to infinity, right? So this is a known result. Therefore, the prior distribution is improper. Jeffreys prior is improper for the Poisson case. And it can be seen as a gamma distribution with parameter 1/2 and the other term 0. Now, when the other term is 0, gamma distribution is defined when both the terms are positive. So this is actually, I'm pushing myself to the boundary. This is not a gamma distribution. In order to define a gamma distribution, both parameters have to be positive. But hypothetically, you can formulate, you can frame this density as a gamma with the first shape parameter 1/2 and the scale parameter 0. Now, what is the advantage if you do that? Then the corresponding posterior for n IIT observations is gamma 1/2 plus n y bar plus n, comma n, because we have seen it that with the gamma prior distribution, the posterior turned out to be this a plus n y bar, comma b plus n. So you plug in b equal to 0 right there, and then you have the posterior density. You do not have to calculate the posterior density afresh. You can use the existing result. And this posterior density, this density is a proper density as long as n is greater than or equal to 1, regardless of the value of y bar. So what you see is that although the prior was improper, but the posterior was proper. Questions? Next, Jeffreys prior for Poisson. Why have we considered a single Poisson observation for deriving Jeffreys prior? You see, you may have noticed already, I said, let's consider a single observation and calculate the log likelihood and derive Jeffreys prior. The answer is that whether you consider a single observation or all n observations, the answer remains the same. Note that Jeffreys prior is simply proportional to the square root of the information matrix. And let us calculate Fisher information for a single observation, say y1. And this is that, let us call it I0 theta. And so Jeffreys prior based on a single observation is square root of I0 theta. This is based on a single observation. Now let us calculate Jeffreys prior based on n observations. If it is based on n observations and based on IID observations, what happens? Your log likelihood then consists of n components, and you take out these components summation outside and take expectation of every component, and it turned out it is n times I0 theta. So information matrix information for a single observation and based on n IID observations, they are proportional. That is the bottom line, because when you take expectation, there is no distinction between whether it is calculated based on the first observation, second observation, third observation, or the nth observation, because you have already taken expectation. So Jeffreys prior based on n IID observations is square root of n times I0 theta, which is also proportional to square root of I0 theta. That is the bottom line. And for our easy calculations, often we work with single observation. Single observation, and single observation means you just assume x is a single value and calculate log likelihood, derivative, double derivative, and then take expectation. And both methods give you the same expression, same result. In our next lecture, we'll talk about use of Jeffreys prior for this number of blemishes. Questions?